Okay, so today, in my continuing quest to deviate from the standard plan, we are going to learn about Charles' Law today. Bruh.
I was studying last night. I
Bruh.
was telling you.
Bruh. So today is Charles' Law. We're going to talk about what this is. We're going to talk about specifically the parallels from Charles' Law to what we described yesterday with the combined law and then also Boyle's Law. So make a small heading for Charles' Law, and that's about as far as we're going to go with the spreadsheet for now.
What's a balloonist?
I'm sorry? A guy that travels in balloons.
Does he like make maps and stuff?
Probably. Did some cartography along with his balloonist-ing. Yes, that's what it was. He was a balloon animal expert. No.
A lot of people used to do it.
He did like hot air balloons, like when hot air balloons weren't a thing yet. Balloonist. Not a clown balloon guy. So anyway. All right, so if yesterday, what two properties of a gas did we relate to each other? Volume and pressure. That was Boyle's Law. Okay, volume and pressure. Today, we're going to do something different. Helgeson, you're on the camera, so we need you to follow me for today. Or we're going to do a thing, so you need to document it. We need you here. We need you. We need you. Make sure Henry is not in the video. All right, so if yesterday was pressure and volume, today, let's see if you can guess. Today is going to be volume and what? Nope. Temperature. How can you tell? So before you guys were in here, I had grabbed a Mountain Dew can, and I put a little bit of water in this, maybe a centimeter or two of water inside the bottom of this, and I put it on a hot plate, and I'm heating it up. And then what did I put in here? Ice. So we are going to do the relationship between volume and temperature today. Okay, volume and temperature. Let's make a prediction before we actually do a thing first. What's in this can right now?
Steam, water.
Not Mountain Dew.
Water vapor.
Not Mountain Dew. What was that?
Water vapor.
Water vapor, also known as?
Steam condensation.
Well, water vapor, sure, but this particular water vapor we would probably call steam. Right? You guys can hear it boiling in there. It's been on this hot plate for a minute. So what's the temperature of the steam inside this can?
212 degrees.
Hot. Henry, we wouldn't use freedom units in here. What's the temperature? Celsius. Yes, it's 100, maybe more of temperature in Celsius. What's the temperature of this ice water? Cold, also 0. So what is your prediction of the relationship between volume of a gas and temperature of that gas? Now remember, relationship yesterday, what was the relationship between pressure and volume?
More pressure, less volume.
Less volume, which we called what kind of relationship? Inversely proportional. What do you think about temperature and volume now?
Less volume, less temperature.
Less temperature, less temperature, less volume. And what is that relationship called?
Inversely proportional.
If it's not inverse, it's verse. No, not. Starts with a D. Directly proportional.
Oh, I knew that. I said that.
As one goes up, the other goes up. As one goes down, the other goes down. So what is your prediction on the change in volume if we suddenly decrease the temperature of this gas?
Crumple into a very small piece. Oh, wait. You have to look at it? Or
I don't know. Are you going to be able to catch this? Is the camera going to be in?
Camera, hold it up. You gotta hold it. You're a really bad gamer.
Ready?
Yes.
You guys can move if Helgeson is in the way.
Will I be able to see it from here?
No.
Maybe we got
Totally going to be able to see it from there. I know.
Yeah, Miranda's so smart.
I know. All right. Ready?
It's gonna blow up. Oh!
Not blow up.
Oh, implode.
Implode.
That's what happened at Summer Reed.
Here is our can. So why did that happen? Yeah, so when we take the temperature of the gas in here and suddenly cool it, right, the volume of that gas suddenly also did what? Went down. And because it was an aluminum can,
Wait, so if you put it back on the thing, will it get big again?
yes, but what would we have to do to make that go?
Put more water in there.
No, yeah, we'd have to add water, and then what else? We'd have to seal this in some way, right? Because then the gas in here would expand as it got hotter.
Could we do it?
Since I had the lid off of this,
Could we do it?
it would just go. No, I don't have no way to seal this.
You know, like
Get some tape.
Duct tape.
Get some tape.
No,
Flex seal?
Just put your hand over it for a little bit.
not a great plan.
Flex seal?
A
Flex
hand
shot?
over something burning. All right, so reset us up. We're going to do the lecture next. All right, so just like we had yesterday, where we had an inversely proportional relationship and we ended up with a formula, Charles' law is going to be similar. I suppose I can do this. What button do I want to hit here? This. So Charles' law gives us a directly proportional relationship between volume and temperature. Volume divided by temperature always equaled some constant K. Don't write all this down, just write the Charles' law, V over T equals K. For now, that's all you really need to know. And this whole slideshow is posted on Google Classroom too. So if you want to get crazy, here is the definition of Charles' law. And there's something in there that's kind of interesting that we're going to talk about in just a moment. At constant pressure. So, does anybody have Boyle's law nearby? What was constant for Boyle's law? Temperature. The temperature we assume to stay the same. So, for Charles' law, we're doing the same thing with pressure. I'm going to say the pressure remains constant, but now we're talking about the Kelvin temperature and the volume being directly related. And now, just like we had yesterday, we're going to have the form of this equation that we are going to use to answer questions and do homework and stuff. So here it is. Where yesterday we had P times V equals P times V, now we have V over T equals V over T. Your initial condition, and then your changed condition, or your final condition, or whatever. Now, there is a problem with this that we need to address. So I wouldn't worry about the paragraph as much as I would worry about the V over T equals V over T. So a moment ago, we had our Mountain Dew can. What was our initial volume? Anybody remember what I said? Ethan, would you read the volume on that Mountain Dew can for us? There's a volume, right? Yep. Might be hard to read now. I screwed that all up. 355 mils. What was our initial temperature, did we say? 100 degrees Celsius. What was our volume 2? We're going to call that our question mark. What was our temp 2? What was our ice water, our ice bath? 0 degrees Celsius. So let's plug that in for the sake of trying this. 355 over 100 equals V2 over 0. So I'm spotting some problems here. Divide by 0 kind of makes me feel nauseous, but let's try it anyway. How do we solve this problem? How do we solve a problem like this? Cross multiply and divide, right? We've seen that before in this class when we did, I think, percent yield or something. So let's try that. So 355 times 0, 0 divided by 100, V2 equals 0 mils. Is that possible?
Yeah.
Is it though?
No.
Is it though?
No.
Can something with mass have a volume of 0? Sure, but there was definitely steam in there, right? How could that possibly have a volume of 0?
A black hole.
A black hole. We tried that yesterday. So you cannot have this.
What about a vacuum?
Still not 0.
It doesn't have mass.
You would 0 volume is fine, but there could not be anything in it. As soon as there's something in there that can't have a volume of 0.
That's what I mean. If everything was sucked out.
True, but we're talking about a sample of gas here. So yeah, if there was no gas in there, then it could have a 0 volume, but then we wouldn't be talking about that. Let's think about this another way. What if we, instead of doing an ice bath, what if we had a really cold day in the winter and our temperature was negative 10 degrees Celsius? Negative 10 degrees Celsius. Let's sub this out and do that. Negative 10. Cross multiply and divide. At least we're going to get a number now. 355 times 10 divided by 100. 35.5 negative. Volume 2 equals negative 35.5 milliliters. Can we have a negative volume? If we can't have a 0 volume, we surely can't have a negative volume. What would negative volume mean? It would be our black hole from yesterday. So we are not going to create a black hole here in this classroom. We definitely did not do that. We would all have noticed had we accidentally created a black hole in class.
Can we make a black hole?
Sure.
How?
No.
I think Hawking's lab is
So in the definition that you wrote down a moment ago, what word was in there that looked a little funky? Temperature in what? Kelvin. Very nice. Thank you. Yes. So in our definition a moment ago, this word here is the asterisk on Charles' law. We have to measure temperature in Kelvin units. Does anybody remember the Kelvin scale? What's significant about the Kelvin scale? I like what you said before. It's always positive. Kelvin temp starts at 0 on the temp line at absolute 0. As cold as anything could ever get is absolute 0. That's the 0 point for Kelvin. Everything in the universe is something, it has a temperature higher than absolute 0. Everything. So you cannot have a 0 Kelvin temperature and you cannot have a negative Kelvin temperature. So that solves our issue. The problem is that we then have to convert any temperature numbers that we might have into Kelvin units. Yes, sir.
What's the closest you can get to the absolute zero?
Experimentally, we've gotten within 0.001 degrees of absolute zero. But absolute zero is defined where matter would cease to have any kind of movement or kinetic energy. We don't believe that's theoretically possible.
Okay.
Helium solidifies at like a degree or so above absolute zero.
Okay.
That's how cold you have to get helium to get it to be in its solid form.
How would you do that?
Yes. Technically, how they do it is they use liquid helium and they expand it and that draws heat away. It's complicated. All right, so now we can do this. We just have to convert. So you're going to want to write down the conversion from Celsius to Kelvin. Kelvin. So this is the equation you need for converting between Kelvin and Celsius temperature. So many equations indeed. They're all easy though. These are easy equations.
That doesn't seem
Never thought that would
like it
come out of
would
my mouth.
work. But if it's like negative 300,
It wouldn't be negative 300. You can't have a negative 300 Celsius degrees.
it would be negative 7, so I'll find that.
So what is our temp 1 in Kelvin units? And what is our temp 2 in Kelvin units?
There you go.
Now we're using negative 10 here, but our experiment was actually at 0 degrees Celsius. But I had 10 written on the board. Maybe we should do the real one that we did. Maybe we should erase this. We had all agreed that our temp 2 was 0 degrees Celsius equals 273 degrees Kelvin. So now let's plug this into our formula. Volume 1 was 355. Temp 1 was 373.
Wait, even if it's like positive, you still have to change it?
Yes. We're going to talk about that in just a second. This math, this conversion to Kelvin, has to happen every time you use Charles' law. Whether the numbers are positive or negative or 0, it makes no difference. To do this math, you have to convert to Kelvin units to do the math. Somebody give me an answer here.
Wait,
What was that now?
259.8.
259.8? So from 350 to 250 something, does that seem plausible? Sure. I agree with you. I think it definitely shrank by at least 100 mils, if not more. We're assuming 100 and 0. Those numbers might have been slightly different. We didn't measure those with a thermometer or anything else. So this is Charles' law, and this is conversions to Kelvin, and back and forth. And now I want to come full circle here. We had the combined gas laws, what we started with yesterday. Anybody remember what that looked like? So, what did we say was constant for Charles' law? No? No? What didn't change? What did we assume remained consistent for Charles' law to work?
the amount.
Temperature and volume.
Density.
Constant Pressure. So again, if we started with the combined law here and we eliminated pressure because it's the same, guess what we end up with? We end up with Charles' law. So this is how these are all related. Full circle, indeed. This is not negative. Don't get crazy. So this is how these are all related. If pressure is held to be constant, that means the pressure number would be the same on both sides. Mathematically, we could just eliminate it. You just get rid of that variable since it's the same. They would cancel out. And then you end up with Charles' law.
Yes.
Just wait till tomorrow. I'm going to undo this and put this back in. Tomorrow, when we talk about one more of the combined laws, guess what we're going to hold constant? Volume. Guess what the resulting equation will be? P divided by T equals P divided by T. So that's your preview for tomorrow. So, today, homework is